Oh, good morning, everyone. I wish I had a little bit more time. I thought I was going to score some time, but I'm going to talk about the deposition work that we've been doing the past 2 years, from 2021 to 22. Just a little bit of background. What we found was that macadamia farmers use a variety of application methodologies, from hydraulic pressure sprayers to air-assisted high and low profile sprayers all over the bank. It's what we call a UBO phenomena, the unidentified blowing object phenomena. And we couldn't get a little bit of clarity of what's being used where, what's the direction that the industry is going. And also in terms of, if we talk about big trees, quite various volume ranges. And those volume ranges are broken up into specific droplet spectrums. Anything from 540 liters per hectare on really big trees, 8-meter trees, that's 8 meters high, 6 meters wide. So it was very interesting to see the variation. These methodologies do give you guys unblemished-free nuts, or blemish-free nuts, and it protects it from pests and diseases, and you guys get to export and make a profit. The question is it working? It's difficult to see out there. But what about optimizing the application process? And if you look at that matrix on the screen, is what we call the application matrix, and those are all the factors that you need to take into account when optimizing application. It's highly variable. Not giving enough attention to any one of those factors can influence application. At the end of the day, you won't get optimal application. And usually that leads to the snowball effect of there's too much to focus on. What I'm doing is working, so I'm going to continue working with it because it's working. And I do agree, it's working, but the question is always, can we improve on it, because it is inefficient. There's a lot of money that you can save, a lot of less environmental impact that we can have a result of that. And if we talk about inefficiencies, I'm just going to name a few with the work that we have been doing. Usually it's because of poor application methodology. That is the wrong applicator for the wrong type of tree, too low sprayer speeds or too high sprayer speeds, too low air volume, too high air volume or no air, or too low spray volumes. You need a certain amount of droplets to cover a certain volume of material. You're not going to get away from that. For example, this is a spray that we did, just a trial plot that we did at around 500 liters of water per hectare on a really large system, and the deposition was really inadequate at that specific dose concentration that we used. Again, that can be the opposite, where you have large losses due to runoff and drift because of too high volumes. For example, that you guys are seeing over there, you can see at the tip of that leaf the amount of runoff and accumulation that's happening there, and that usually carries over to leaf burn. And you're stripping that whole leaf of the amount or the quantity of active that you landed and realizing a really poor quality of deposition. This leads to other inefficiencies, for example, a high fuel, time, and labor cost. The more time you spend in an orchard, the more money it's going to cost you, and the bigger is the chance that you need to get back into that orchard to respray because your timing was bad. And actually that also can head to contamination of the operator, the guy that's actually doing the work, the equipment that we're using, and soil and water that we need to protect. So inefficiencies can be high if we don't optimize. So can we be more efficient? I definitely think so, through the work that we've been done the past 2 seasons. And will it work? Yes, I definitely think that we can get better disease control by implementing some of these methodologies. And the big thing is also, where do you start when you start working in optimization of application? Do you get 10 sprayers out there and pull them next to each other and start spraying, and just this is the best spray, and everybody's going to call you after that and give you mulekite because you said that guy's sprayer is better than that guy's sprayer? That's why with deposition work, we always start with building baselines. We start small and we see what the effects are. And learning from all the other crops that we have done optimization in, from citrus, apples, pears, plums, prunes, blueberries, the latest pecan nuts, the best way to start is to choose effective water volumes and water volume ranges, build that baseline, and see where do we go from there. What are the next points that we need to focus on? And that's what we looked at. We looked at variation in spray volume and specifically how the macadamia tree influences the deposition factors. And we did this specifically in a dense and a less dense orchard. The dense orchard was a Beaumont of cultivar. It was 8 meters high, 6 meters deep, and had a row spacing of 8 meters. And we calculated that the tree row volume in liters per hectare that was needed to spray that type of tree or that volume of tree to the point of runoff using a formula that we call the Sutton and Unrath formula. The specific formula calculates what is the amount of water that is needed to spray a block to the runoff, and it uses the concept that you need 93.7 liters of atomized spray water to a fine and very fine droplet spectrum to cover 1,000 cubic meters of material. The sparse canopy that we sprayed was a CV7029, exactly the same specs. For the specific trial, we set up the sprayer using canopy adapted spraying. This is a methodology that all of you guys probably know of also, but this is where we match the air volume that's being put out by the machine and the air speed to the amount of volume of material that we need to cover to maximize the amount of droplets that are intercepted by the canopy and to minimize the amount that we're losing due to runoff and blow through or blow off. For the specific trial, we started with one system. We specifically used the aerobic Lear's even flow with a high pitch, blade pitch that produces a high enough amount of air, because this is a system that we've built a lot of our trial sets on, and from there on you can move on to other systems. Through canopy adapted spraying, we determined that the most optimal speed for the specific trial was 2.4 kilometers per hour. And using that tree row volume, we decided on 4 specific volume specs that we're going to build the baseline on. That was 1,250, 2,500, 3,750, and 5,000. And the volume was manipulated by changing nozzles to keep the droplet size the same, keep speed the same. So every time we just take out the nozzles, and to keep the amount of influencing factors in these data sets to a minimum. Because as you're going to see, deposition data gets quite complex, and to read into it to see what is going on there. All of these trials, we usually use a yellow fluorescent pigment as a tracer. This tracer shows you where the specific fungicide or pesticide is going to land on the target. We're not looking at droplets, we're physically looking at where are the active ingredient laying on the target. And what is the chance then that an insect or the pathogen spore is going to get in contact with that. For this specific trial, we dosed at 1 ml per liter, and we kept that solid straight throughout the trial. So we didn't increase concentrations at the lower volumes. For the next set of trials, that is the next step that we're going to do. We've used this methodology in various other studies that we've published, and it's a very good way to evaluate deposition. So how did we do it? We sprayed 10 trees from both sides, and we repeated that by 3 reps. So it's a total amount of 30 trees that were sprayed per treatment. And then for each treatment, we selected 3 trees out of one of those reps, and then we sampled leaves from the top, the middle, and the bottom of the canopy. The height restriction we put there was 8 meters high on the inside of the outside, so you create a good spatial map of what is going on in terms of deposition inside of the canopy. We then flew the leaves back down to Cape Town, or Stellenbosch, to the lab, where we digitally photographed it with a high-end camera whilst being illuminated by 2 365 nanometer mid-lights. This basically activates that tracer molecule on the surface so you can see specifically where it lands. Those digital photos, we run then through the software that was developed at the university specifically to determine the deposition parameters on that leaf surface. And we can do this for fruits and all kinds of, and hopefully one of these days for flowers. But it's very accurate. The digital images has a very, very high quality, so we can literally pick up each of those particles that's landed on the surface. So when we look at deposition data, it's important to quantify what we're seeing in relation to not only deposition, but also to crop protection. So what you're looking at there is specifically those particles lying on the leaf surface. And when we talk about deposition quantity, we're talking about the amount that was landed on the target, and this is expressed as a total percentage of the area of that leaf. Now, interestingly, the leaf that you're seeing there with that amount of deposition on it is around 5%. That's what you've landed on that target surface. So if you take that active, you push it into a corner, it's only going to cover a total of 5% of that leaf surface. And it's actually a lot. It's all about how well that 5% is distributed over the target surface. And that is what we call the quality of deposition. So specifically, how we measure quality is we put a digital grid over the leaves. We determine the quantity in each of those blocks, and then we vary specifically each of those with each other. And we're looking into new methodologies to evaluate quality, specifically looking into AI, which is very exciting in the future. But if you look at that leaf surface over there, it would have a bad deposition quality because you already started to get blotching and runoff, so it's pulling all of that active to specific spots on the leaf surface, and you get open areas which is not protected. Lastly, and very important, we look at the variation in deposition. Variation in deposition is where we look at how does one leaf vary from the next, for example, in a 15-leaf batch. In application, we want to land the same amount of active and the same quality on each of those targets because each of those targets needs to be protected. The way that we apply it is going to make that vary highly or less highly. And we're always looking there for a low variation uniformity value. Okay, but I'm a plant pathologist. Usually when you get guys coming to demonstrate sprayers, they always spray a dye and it looks great under the lights and everybody's excited. The question always is, what does it mean? What does that amount or that what I am seeing on the leaf surface means? And that's why over the past few years at Stellenbosch University, a colleague of mine together with Adele, they developed this specific model for apple scab on apples, and specifically with the use of mancozeb. So what is the deposition quantity that you need to land to get a certain percentage of controls? And then we can relate that back to deposition quantity. And for mancozeb, which is quite a good contact fungicide, that's around 1.35% that you need on the target surface. I, way back in the day, did it on copper oxychloride, which is not such a good fungicide, and we determined that you need about 4%, 4.14% particle coverage on the leaf surface to achieve only 75%. And we did this on citrus, specifically for Alternaria alternata, part of our C3 control on mandarins. So this gives us a very good idea of where we need to be when we look at deposition data. So to be safe, myself and my colleagues, we always say that we want to be above 4%. If we can achieve above 4%, we're good. That's going to be influenced by a few things. And specifically in this trial, remember we only sprayed at 1x, so 1 ml per liter. It's going to vary with the amount of water volume that we sprayed. So if we look at the data sets that I'm going to show you now, we're going to look at the dense canopy on the left-hand side and the sparse canopy on the right-hand side. This is for 2021. At the bottom, those are the volumes that we sprayed. We're looking at deposition quantity, that's the value. And we're looking at the inside of the canopy, that's the white bar, and the dark green bar or darker green bar is the outside of the canopy. So first of all, if you put in our benchmark line where we want to be above, you'll see that none of the sprays that we applied there, concentrated in the way that we applied it, actually achieved a value above that 4%. Only at the sparse canopy, above 3,750 liters of water per hectare, we actually landed above that. Very interestingly also is that in the less dense canopy, on the sparse canopy, we landed much more active on the inside of the canopy and on the outside of the canopy. And we see this a lot specifically in dense canopies. Interestingly, second, or what we also saw was that at the higher volumes, and usually this is something that happens out in the field, and specifically in citrus production, where more water usually equates to better penetration, which is always not the case. Penetration is a factor of how well aerated that canopy is and how it's going to allow specifically droplets into the canopy, which is very evident from the data that we collected here, where the dense canopy at the same water volumes almost landed half of what you did specifically in that more open canopy. Sparse canopies gave us better penetration right through, but interestingly, if you look visually at the leaves that we photographed, we found that we already achieved runoff at volumes above 2,500 liters per hectare, and that was specifically seen on the outside of the canopy. So if you compare your inside deposition to your outside deposition, you always want, and you will always get, more deposition on the outside of the canopy because it's the first leaves that intercepts droplets. As you go higher, you will see that value change over, with the inside all of a sudden getting more deposition. And why is that? That's because of runoff. So there was a high loss already on the outer canopy leaves due to runoff. You're literally losing that amount of active in relation to the 2.5 to the outside of the canopy, which is inefficient. And this was the same for the 5,000 liters per hectare spray. And this was more evident in the dense canopy, where we started seeing that already around 1,250 liters of water per hectare, right through the spectrum, switching over also around 3,750. So what about concentrate sprays? If we go that route one day, and hopefully you guys can also start doing that as soon as registrations allow it, this is how we spray mostly in apples and pears. We will spray a 4x or a 3x application at lower volumes with a droplet density that's more than enough to cover the canopy. But I put in some theoretical values there. We've got a formula that we use to calculate that, and at a 2x or a 3x at those lower volumes, we will have sufficient deposition, hopefully, to get just at that 4% where we want to be. The risk there is runoff. Because we saw runoff so early, because of the structure of a macadamia tree, you always run the risk of leaf scorch or burn as soon as you're going to go and up that dose with specific active ingredients. So the next factor looking at is the top, the middle, and the bottom of the canopy. Also, again, at deposition quantity. And what we found there is that I think the most interesting here is that we had very, very poor deposition in the top, and I think you all are very familiar with that, depending on the system that you guys are using. But this, remember here, we use the same nozzle from the top to the bottom of the specific sprayer that we use to keep variation as low as possible. And you can amend this by changing the ratio, specifically of volume output on the back of the system. This is work that we just did now on a while back on pecan nuts. We're already in that stage where we are evaluating systems for the industry. This was sprayed at 1,500 liters of water per hectare. It's really big pecan nut trees. Looking at the top, middle, and bottom, this was a 2x spray at 3.45 kilometers per hour. And there we changed up the specific variation in nozzles and improved the deposition in the top of the canopies at 8 meters drastically. Interestingly, there's a very good article out in Plant Disease where the Americans also evaluated specifically pecan scab infection, and they found more or less the same that we are finding in our research on high crops, that as soon as you go above 8 meters with tree growth, deposition drops drastically, and there's very little systems or energy efficient systems that can produce enough air to get yourself up above that 8 meters, and usually the uniformity of deposition drops off. And this is what I want to show you guys here. So this is deposition uniformity, so it's the variation in deposition between leaves. And as you can see, right through, the percentages were very high. None of the variation between leaves was above 50%, below 50%. So all of them more than 50% variation from leaf to leaf to leaf. So if you've got 15 leaves, the deposition quantity is varying very high on those specific surfaces. We can ascribe that to the high minimum significant difference that we found in the stats. That was about 3.4%. So from leaf to leaf, it's differing quite a lot. And it's the macadamia tree. It is a complex target to apply active ingredients onto. It is going to be complex, and there's a lot of work that's needed to sort this out. And the top of the canopies, the uniformity was much lower, and the higher your tree is going to be, the higher the variation in deposition in the tops is going to be. Looking at the 2022 data, we immediately saw an improvement, specifically in application. We basically repeated exactly the same trial in exactly the same orchards. The difference being that both of the canopies had some light work done to it, specifically aerating the specific canopies. And that immediately improved penetration and deposition on those canopies, realizing less runoff on the outside, better deposition on the inside, to such an extent that the sparse canopy and the dense Beaumont canopy almost realized similar deposition quantities. However, the trend was still the same, where above 2,500 liters of water per hectare, we started seeing a lot of runoff and a change over from higher deposition on the inside and on the outside due to runoff on those specific canopies. This makes it quite difficult to start looking at where is that optimal volume specification that we need to be at. Again, on the top of the canopies, we saw the same, lower deposition, and here we got in a high tower sprayer, a 4-meter tower sprayer with a very high air column, and it's a well-designed tower. We sprayed it at the 2,500 liters of water per hectare, and that definitely did improve deposition a little bit, as you can see right over there and right over there. but it wasn't a lot in relation. You pushed it basically from, let's say, 0.3% FPC to around, I think it was just above 1.8%. So still very low, still very high variation in deposition. Nozzle arrangement, again, can improve that, but I think there's still a lot of work to be done. I don't think concentrating on machines that can spray above 8 meters is worth it. Okay, so from the data, what have we learned so far? Definitely that the optimal spray volume at 1x concentrations at these large trees that we applied on, those 8 meters by 6 meters on 8 meter rowers, was around 2,000 to 3,000 liters of water per hectare. However, we found a sufficient droplet density. There's enough droplets at around 1,500 liters of water per hectare. And that is where next steps in research should focus on how can we improve that even more and focus on concentrate spray so that we can carry more active with less droplets and land it more efficiently with less losses. Too low volumes, definitely with our pilot trials, we saw that there's a high variation in deposition and one should rather go to the higher end than the lower end. And that higher water volumes above that 3750, specifically for light sprays, is super optimal and you will have a lot of losses. There was high variation in the data. We ascribed this specifically to the macadamia tree. There's many targets, leaves and nuts, that need the canopy that the active needs to be distributed through. It's complex, so it's not easy to reach those targets. So optimization is critical. Out of the amount of work that we have done, we know that high-profile sprayers, which have sufficient air assistance that is well designed by well-known engineers, is very, very important to be effective in terms of application. Air assistance is important. In terms of that, also the optimal nozzle selection and taking care of your nozzles is also very important. Don't change them every 4 years. Change them when they need to be changed, when their variation is off by 14%. Layout of those nozzles specifically to concentrate a higher amount of the volume in the top of the trees, that is important to reduce the variation deposition at the top of the canopies, and you can fine-tune it even more specifically. Canopies, Macs aren't easy to spray, definitely not. It's probably one of the hardest targets that we have done work on. The canopies can be very dense, and that is going to complicate penetration. You cannot spray into a canopy if there isn't sufficient windows there. Around enough amount on the outside is going to increase. So what's next? Specifically what we're working on now is doing what we've done for the pecan nut industry. We're using this data to write specifically a 3-row volume model, for example, that we're using in apples and pears and now in pecan nuts. Basically what we're doing, we're fine-tuning the data sets so we can find that optimal volume, so we can recalculate or calculate back what is the optimal volume per 1,000 cubes of material that you need for sufficient deposition. And I just put this in an example for the pecan formula they're currently using. It's 10,000 divided by the row width times the tree height and the tree depth times 0.018, and that will give you very good sufficient deposition. So we're looking in terms of that because trees are going to grow, so they're going to be small and they're going to increase in size, and then the model will help to each season determine what that critical optimal volume is for application. Thank you very much. I would like to thank SAMAC for the funding for this project. We learned a lot. We always learn a lot. It was really hard work climbing up on those trees and picking 2,000 leaves, but it was really, really interesting. And also for the farmers, for the systems and the trial sites. Thanks. Any questions if there's time?
Gideon, we're running out of time, but I'll allow one question. I'm sure there's lots of questions here, but there's a hand. No, there's two hands.
You mentioned hazard, spray concentration, and then you also mentioned we got a challenging crop with its canopy and its growth characteristics. So how are we going to achieve this concentrated spray? I'm interested to hear how you guys would.
So
obviously we're going to prune accordingly every season, but still it's a big, dense bush, no matter what way you look at it.
So the idea there is to go and do concentrate trials with some active ingredients that we know can cause some damage and see what the effect is. As I mentioned on On apples and pears, prunes and plums, blueberries, we're doing concentrate sprays very effectively. For example, on a 2000 TRV apple orchard, we'll spray 500 liters of water per hectare at 4x the concentration. The big thing is we're not getting runoff, so we're not getting that damage. So that's something that we need to look in, yeah. Yeah, even for our citrus trees down in the Cape, there's a lot that we handle like that also, where we have Spanish vase, open trees with a lot of depth and density, that we get away with that, yeah. So that's definitely something that we look into.